In this video, we are going to talk about correlation and regression. If you haven't done so yet, go ahead and press pause and read the correlation and regression brief. This lecture kind of builds on that written introduction. So let's start with a simple scatter plot. We have here baseline axial length along the x-axis, and we have axial length at 5 years on the y-axis. And these are data from an orthokeratology study in which subjects either got one type of lens, a spheric, or another type of lens, spherical, and then they wore them for nightly for 5 years, and with the purpose of controlling myopia. In this case, this graph, we're just looking at the spheric design. Each point here is a person, a patient, a child. So for example, this child at baseline had a 24, and after 5 years his axial length shrunk to 23.5. Now your axial length doesn't shrink usually, so this is probably a measurement error. Here we have a person who had maybe 25.5, and after 5 years his eye grew to be 26.75 millimeters. So the scatter plot is, we see here is this sequence of dots, and you can see that these dots kind of cluster along their pattern. They're associated. The higher the x-axis, the higher the points on the y-axis. So it has this positive relationship. And we measure this association, or this relationship, with a Pearson correlation coefficient. In this case, the R is equal to 0.94. And that's a pretty good relationship. Now, generally, when we speak of correlations, we refer to R squared, and that's simply 0.94 squared, gives you 0.89. And that refers to the percent of variance accounted for by this relationship. So the next thing we can see here is this red line. Now the red line is a linear regression line. This line differs from the black line. The black line is simply a line of identity. So if you were at baseline at 23, the point on this line would be at 5 years 23. Here it's 28 and 28. So the line just says how you grew, and most of the dots on this line are above this line of identity because the eye grew. Now I can't really say why there are a few points below, but I'm calling it measurement error, but you know, who knows, maybe they did shrink a little bit in this particular case. Unlikely, but possible, I suppose. Now, regression refers to the relationship. It formalizes it into a formula with this straight line. In this case, y, which is the 5-year axial length, equals y equals bx plus a, where b is the slope, 1.04 is the slope times x, and a is minus 0.52. And so we could predict, the idea is to be able to predict from baseline. If we had somebody with a baseline of 26, we come up to this red line, and by plugging 26 into this x value, multiplying times 1.04 and subtracting 0.52, we would get a number close to 26.5. So one of the big purposes or reasons for people recording relationships like this is to enable you to predict what might happen in the future with your patient. Now, not all the points fall on this line. This red line is the best fitting line through all of these points. It uses a method called method of least squares, and it finds the point where the residuals are minimized, and the residuals are the points. So for a patient, this patient had a 24 baseline, was predicted to be 25.5, or no, was predicted to be 24.5, but was a lot higher at 25.5. So this difference from this line to this dot, that's called the residual. And the closer these points are to the line, the higher the proportion of variance that's accounted for by this line. For here we have a little box plot that shows the maximum y and the minimum y, and most of the values, there's a median that's around here, most of the values fall within, 50% of the values fall within this area. So it goes over to 25.75, 24.25, most of the values are falling in there. But if you are going off to the sides too, and this is the total variance in y, and the model is able to account for 89%. That is, that line in its steepness with the residual not falling very far off of it says that our model predicts 89% or 0.98 or 0.89 proportion of the variance. This is a very tight and good model. The beta coefficient, the 1.04, that B, when we test for significance there, we're testing if B equals 0, and then we get a standard error, and it's a pretty easy, basically a t-test of 1.04 divided by the standard error of this B, and that's a t, and this would be p less than 0.001. It's highly significant, and what that means is that the probability of getting a beta or getting a t statistic is pretty small when you have a b this high over the small, relatively small variance around that line. So regression is basically that. Now, there are occasionally some things that when you're reading the literature you have to take into account. In this case, these numbers right here are exactly, they go from, like 6 to maybe around 20, 6 to around 20. These are a subset. These are a subset of this longer value. Now what happens in studies is that people look at normal. They do a study on optometry students or on normal patients in the clinic, and they want to compare two measures like Goldman IOP and DCT, which is another test for measuring IOP. And here the R squared is 0.4. The exact same data, but adding these other patients that have higher IOPs, give an R square of 0.59 or almost 0.6. 60% of the variance compared to 40%. And that's due to this problem called range restriction. You're only looking at remember, the idea is to account for variance. Well, the variance is just in this range here, from say 6 up to 22, whereas over here the y variance is from 6 up to 30. And because you have more variance to account for, if your model is good, you can account for more variance. So be careful when you're reading the literature and they're using normal patients, non-diseased patients or optometry students to compare the similarity of two measures. If they're just using healthy subjects, they're going to underestimate the goodness of fit for this. Now, if we recall, our R that we were talking about was 30% the effect size, 30% we wanted to see things. If we're talking about, or 0.3 for an R squared would be 10%. So this is good from a theoretical point that Goldman is predicting DCT. But from an instrument point of view, the similarity is not really quite as good, because remember, we wanted values that are supposed to measure the same thing. We want them to correlate around 0.9, and 0.9 squared is 81%, and the variance is only 60. So the relationship between Goldman and DCT is actually not that good. If you measured a patient's IOP one day with Goldman and another visit with DCT, that would not be a good idea, because they are not they're not that associated. You wouldn't get the relative change that you would want to, and that's why in the guidelines for general clinical care, the AOA's guidelines, they tell you if you're going to measure IOP, you should do it twice, and you should be consistent with one measure or another. So consistently use DCT for your patient or consistently use Goldman, but don't mix and match, because they're just not that well related. So range restriction, big issue. Finding measures that are correlated, and for different instruments. You got a new instrument, you start using it in your practice, but it could be different from your old instrument. So be careful when you're transitioning into the new. Now let's consider a multiple regression model. This was kind of an interesting study. It looked at the relationship between this intrinsically photosensitive retinal ganglia cell, pupil response, and melatonin hormone. Basically, the idea is that the intrinsically photosensitive retinal ganglia cell is a small retinal ganglia cell that can take the light. It determines the light, whether it's day or night, and then it stimulates or it helps control your circadian clock. And when it gets to be nighttime, as nighttime is approaching, light of the day is getting dimmer, it tells your melatonin to start getting bigger or secreting more. And then during the day, it suppresses melatonin. Now, one of the other functions of the IPRGC is pupil response. So when you go outside, it says, hey, it's bright, I'm going to constrict. And then at night, it gets bigger in order to see better. Well, in the case of diabetics, and especially those that have developed retinopathy, that ganglia cell layer is disrupted, and the IPRGC doesn't work as well. And so you don't get the pupil response. And they've done a study to essentially verify that. So in this particular regression equation, they look at the melatonin response, and they take samples from the patient, can determine their melatonin, and then they look to see they had different levels of diabetic retinopathy. So they had patients that were normal, non-diabetics. They had patients that were diabetics with no diabetic retinopathy, and they had patients that were diabetic and had diabetic retinopathy. Notice this is not a randomized controlled trial. This is definitely an observational type study. And so what they found was that the pupil response was disrupted. And now when we look at the relationship between this pupil response and melatonin secretion, we see that the larger the pupil, because this coefficient here is 4.55, that's a positive. So the larger that number, the more melatonin response there is. And this was a very significant finding. Remember, significance doesn't prove it, it just eliminates the chance. But 455 divided by 154 is a t-value in the neighborhood of 3, which is a big t-score, resulting in the probability that you'd find that by chance if pupil response didn't matter, in other words, if the null hypothesis were true. That's a small probability, 0.005. They also noted that insomnia, so there was an insomnia severity scale. Well, this is only 0.08, but basically it wasn't, you can't eliminate chance in this case, but it's in the direction that the more the subject reported insomnia, the less melatonin, the sleep hormone, was secreted. So we have here, and basically what we're doing is we're looking at this pupil response while we're controlling all of these other variables. Now, pupil response wasn't in here sharing some of this other variance. Insomnia severity may very well have been significant. But that's a multiple regression model where you put all of these variables in there. They wanted to control, figured sex made a difference as far as sleeping goes. Males tended to have less melatonin secretion. So if you were a male, you decreased your melatonin output scale by 0.73. Now the reason this is added in here is because that takes care of the variance due to gender. So you're controlling for whether you're male or female by adding this in here. So then you can look at the other variables in the context of having removed gender as a confounder. Same way with these others. So multiple regression, very useful. In the case of this particular study, the melatonin variable was continuous. Sometimes there are studies done where the outcome is binary. Say, let's look at variables that predict the onset of myopia. And you either are myopic or you're not. And that's a similar model, only it's called multiple logistic regression, and these coefficients are interpreted differently, and we'll go over that in a few videos from here. All right. So in summary, regression and multiple regression and correlation, those are all things used to kind of understand the relationships between variables. It's important to remember that the correlation statistic and the regression model from a statistical point of view do not prove cause and effect. We saw, for example, DCT and Goldman were highly correlated, but the Goldman does not cause the DCT score. They're associated. However, in our previous model with melatonin and pupil size, we have an underlying model in mind, and there is a theory as to how those things work. That theory, plus the statistical support, does allow you to make cause and effect inferences. It doesn't prove anything, but it allows you to support your causal model. In this case, by disrupting the IPRGC, you reduce the pupillary response and your melatonin is affected. So that's correlation and regression.